Okay, time for the final video in the series on duration and convexity, or risk measures, with a look at something called key rate duration as well as empirical duration. So all the time up till now, when we've been talking about duration, we've been effectively assuming that there is a parallel shift in yields or across the yield curve. And that is a very limiting assumption. Yields don't necessarily change simultaneously, instantaneously, by the same amount all across the yield curve. The yield curve often changes in ways that also involve a change of its shape, so a flattening, a steepening, or a twist. So this is going to be addressed by focusing on something called key rate duration, which is also known as partial duration. And what it allows us to do is it's a measure of bond price sensitivity but to non-parallel benchmark yield curve changes. We're still, on the topic of curve-based measures. So if you've got the benchmark yield curve, instead of assuming you shift it all by the same amount across the different maturities, you will only be assuming there is a shift to the key points on that yield curve. For example, a specific maturity, like a 2-year or a 5-year, that goes up. And then, so let me write that down. Instead of shifting the entire benchmark yield curve by the same amount everywhere, we only shift key points. Key points are shifted, and we do these key point shifts, we do them one at a time, and we see what happens to the value of the bond or our portfolio. So key rate duration, K, where K stands for the key rate, or a KAF key rate, so e.g. the 2-year rate or the 5-year rate. This is how you should think about the symbol K here, is going to equal 1 and the negative of 1 over PB, the current price of the bond, multiplied by the change in price due to the shift, divided by the scale of the shift itself. Now, the formula is given. I don't think anybody will get you to compute this. It's quite onerous. But as I said, it allows us to pick up what happens when specific yields change by specific amounts on the curve. And what you can do is change the yields at different key points by specific amounts. And if you were to change them all by the same amount, you would actually get a sum that is equal to effective duration. So sum of the key rate durations from K, whatever, 1 all the way up to N would equal effective duration, which is the summary of the price change, the sum of the price change that happens from yields changing by a specific amount all across the yield curve in a parallel shift. Now, just to make you aware, once again stressing that I don't expect you to have to do this, the way we can apply this if you know what the key rate duration is, to basically check what happens in terms of what's going to be the scale of the change to the price of a bond in relation to its current price. So what I'm doing over here is taking this term in the numerator, leaving this in the denominator, but combining them into a single fraction. And this is going to, if you do just a little bit of transformation, equal to minus key rate duration K, effectively multiplied by the delta RK from the bottom of this fraction here. And this is how you can use key rate duration to approximate the percentage change in the full price of a bond, because effectively the term over here, the change in price related to the current price, is the percentage change in price, and we're always talking about full prices in these contexts. Right, so that's key rate duration. The second one that we're going to focus on is something called empirical duration, which is quite interesting. Now, up till now, we've talked about things like modified duration, effective duration, we just talked about key rate durations, and all of those are so-called analytical duration measures. So analytical duration is the opposite of empirical. This includes modified, effective, key rate, right? And the problem here is an implicit assumption that government bond yields and credit spreads or yield spreads associated with bonds issued by entities that are not default risk free, so yield spreads, are independent, which is not necessarily the case, as I will show you in just a moment. So empirical duration, what it does is it uses historical data, observed sort of data, plugs that into statistical models, statistical models, and that historical data and those statistical models incorporates various factors that may impact bond prices, which incorporates various factors that affect bond yields and bond prices. Okay, and the beauty of this approach, or the big sort of benefit of this approach, is that it accounts for correlation between yield spreads and benchmark yields. Of course, when conditions are changing. Okay, so let me try to illustrate the problem. We've only recently discussed effective duration, which was based on the idea that when benchmark yields change, the bond price changes as well. Of course, that's absolutely kind of natural to assume. However, as you will know, if this is the benchmark yield curve for different maturities, and to that benchmark yield curve we always add an element of yield spread, don't we, to get to sort of our corporate bond yield. If that benchmark yield curve changes, if it, for example, drops, why should we assume, I mean, is it fair to assume that this curve, the corporate yield curve, will also go down in a parallel fashion, implying that there will be no change to the add-on element, that's the yield spread? Perhaps the yield spread will also change, and it would not change in a sort of uniform way. This is what empirical duration allows us to capture, because with effective duration, you're just focusing on what happens to the benchmark yield curve and assuming everything else stays constant, especially the yield spread, which is not necessarily true. And an example which your book gives, which your curriculum gives, and then I saw this also appear in questions, is what happens during a financial crisis. Example, in a big financial crisis, what we experience is this notion of flight to quality or flight to safety. Lots of investors dump riskier investments and go into government bonds. They're considered the safe thing, right? So their prices go up, and obviously their yields effectively go down, which is what I drew here. The benchmark yield curve drops, not necessarily in a parallel way, okay, but it drops. However, at the same time, yield spreads go up on the riskier corporate bonds. There is absolutely, when you consider these two effects, negative correlation between what happens to the benchmark yields and what happens to yield spreads. And analytical duration measures fail to capture that relationship, right? They assume the two things are completely independent, one has no bearing on the other. So negative correlation, let me say, analytical duration measures do not capture this effect. What analytical duration measures will predict is that when the benchmark yield curve drops, the yield spread remains constant, and therefore the prediction will be that there will be an increase to the price of corporate bonds. That's absolutely not true. There may be an increase, but there will be two offsetting effects. On the one hand, the benchmark yield curve drops, but yield spreads rise. So effectively, when you consider things from an empirical point of view, where this should be captured, empirical duration will be lower than analytical duration measures, whichever one you would use, because analytical duration assumes a constant spread, and therefore predicts that the corporate bond will drop, or the yield on it will drop, and its price will go up in line with what's happening to benchmark yield curves, yields, whereas empirical duration should spot that offsetting effect, the negative correlation between them, and will not predict so much price change, and therefore not so much price sensitivity in response to a change in market conditions in a financial crisis. So it will effectively give us a measure of more true but lower sensitivity to that change.